Hey guys, at this point we are moving from rotational motion and starting our harmonic motion unit. So with that, our first example problem, we're going to be looking at a spring, and that spring is connected to a block of uniform mass, and we're told that the mass of this block is 1/2 kilogram. Sorry, smudged a little there. And this 1/2 kilogram block, we're told that at time equals 0, it has been pulled out, stretching our spring to the point where our block has been moved a total of 5 centimeters, which is, we're going to call this time 0. So this is time 0, where the block is right there. And we're told that that is moved 5 centimeters, which is 0.05 meters. And then this block, in order to hold it in place at this time, we're told that we require a force at time 0 of 12.5 newtons. And we are asked for a whole series of things that we're going to need to find. And we'll start listing those off. What we need to find here. Sorry, it is quite the list. What to find? We want to find the spring constant of our spring. We want to find the natural frequency of our spring system. We want to find the period of oscillation. We want to find the potential energy of our spring at time 0 before it's released. We want to find the time until, we'll call it an arrow, until delta x is equal to 0. So we're the time to get from here to here. So I guess we can call this guy position 1. So the time at 1 is what we're after there. We are asked for the velocity at time 1. We are asked for the kinetic energy, still on the screen, at time 1. And then we are asked for the position at 2, and we'll say that time 2 is, we're given 0.1 seconds after it's been released. So the delta x at that point we want to know, and then we would like to know the energy. So we want the potential energy at time 2, the kinetic energy at time 2, and the total energy at time 2. That's our list. Not terribly short, but we can start working our way through it. So first thing we're after is this spring constant. And in order to get the spring constant, we're just going back to stuff we did earlier in the semester. So we're going to draw up our free body diagram. And what that's going to look like is we've got our block. We've got nothing from friction. So we have a force. So this is free body diagram of the block at time 0. We've got a force spring going to the left, and we have a force applied at time 0 going to the right, and we have no movement, and I'm going to go ahead and call to the right positive. So with that, I can say my sum of forces in the x is equal to my mass times my acceleration in the x. I have no acceleration in the x, so this is 0. So I have my force at time 0 in order to hold it in place, minus the force of my spring is equal to 0. So my force at 0 I know is 12.5 newtons. And that's going to be equal to my force of my spring. Force of the spring is K times delta X. This K is what I am after. So that, and the delta X I'm given at time 0 is 0.05. So I've got K times 0.05 meters. So my K is going to be equal to 12.5 newtons divided by 0.05 meters. And that is going to give me a total K value of 250 Newton per meter. And that is my spring constant. So 250 newtons per meter. There we go. First piece done. Simple enough. So with this, moving on to our next piece, we want our natural frequency of how this guy is going to move. So in order to do that, we need to have some idea of how the piece is going to move in general. And for that, we're told that a spring has a omega s that can be found based off of the square root of our spring constant divided by the mass acting at the end of that spring. And that is our omega s. So in this case, we have the square root of 250 newtons per meter divided by 0.5 kilograms. And just checking units here, a Newton is a kilogram meter per second squared. That divided by, that whole thing divided by meters, and that whole thing divided by kilograms. So meters are going to cancel, kilograms are going to cancel. I have 1 over second squared. I'm finding the square root of that. That's 1 over seconds, which is going to end up being our radians per second. And that is going to come out to a value of 22.36 radians per second. I'm going to go ahead and put that, we'll call it right here, because I'm going to need that later, and that's not one of the things that I'm looking for. 22.36 radians per second. And now frequency is going to work just like we had frequency working for our rotational motion. So frequency, we want cycles per second. We have radians per second, so we've got 22.36 radians per second. A full cycle, just like a full revolution, is 2 pi radians. So in order to convert from cycles per second to radians per second, from radians per second to cycles per second, I'm going to divide by 2 pi, and that is giving me a value of 3.56 cycles per second, or as they're commonly referred to as hertz. So our frequency, natural frequency of our piece here is going to be a frequency of 3.56 hertz. Okay, and same idea as before when we're moving from frequency to period. Frequency is just 1 over period, or period is 1 over frequency. So instead of cycles per second, we have how many seconds does it take to go through a full cycle, and that is the definition of a period. So we have 1 over 3.56 cycles per second, which is going to give me a value of 0.281 seconds. It's going to take 2.81 seconds to go a full cycle, to go all the way from out to in to all the way back out. That is one full cycle. Instead of a full rotation, it's how the spring is going to be going back and forth. We want the time it takes to start at one position and return to that same position. That is our period. So that's going to give me a value of 0.281 seconds for my period. Okay. That part was a little bit new, but not terribly new, hopefully, because I guess the new definition of omega was new, but we worked with it just like we worked with the omega when we were talking about rotation. So nothing too crazy going on quite yet. Let's look at potential energy of the spring. This guy is completely review. Potential energy of the spring at time 0. Potential energy of a spring was 1/2 k delta x squared. That's just what we were given for the equation from an earlier unit. And that value is going to come out to 1/2 250 newtons per meter, delta x of 0.05 meters. That value is squared. And I get a value, so newtons per meters times meter squared is going to be a newton meter, which is a joule. So that is going to give me a value of 0.3125 joules. So that is my potential energy at time 0. 0.3125 joules. Okay. Now for the biggie that we spent most of class talking about. We want to know how long it's going to take to go from here and make it back to here. So with that, we are going to, well, actually, with that, we can do it a couple of ways. The simpler way, and that's what we're going to do for this one. We'll do the other way when we get to this unknown number. So the simpler way is it takes 0.281 seconds to go from here all the way back and then all the way back. And half of that time is going to be spent getting there, and half of the time is going to be spent getting back. And half of the time it's going to take to get to the center is going to the other side, because we have a consistent system. So what we can do is we can say that our time to go from 0 to 1 is going to be equal to 0.281 seconds divided by 4. And that's going to come out to approximately 0.07 seconds. Technically, that's a fourth of 0.28, but we're getting into very small decimals at that point. The other way we could do this is I will just go ahead and put this up now. We can say that our equation for a spring position over time, so our x at time 1, is going to be equal to A times cosine of omega t plus phi. And what we've been told is phi is the change in displacement for where we're starting at time equals 0. And phi is 0 when we start with our spring all the way pulled out. In this case, we are pulling it all the way out. We're not then chucking it further. We are pulling it out and releasing it. So our maximum position is at time equals 0, which means that this piece right here is 0 for us. A is going to be our amplitude, which is our maximum displacement. Our maximum displacement is that 0.05. X at 1 is when we get our x back to 0, so this guy is going to be 0. It's going to be equal to 0.05 meters times the cosine of omega. Omega is our omega for our spring. I probably could throw that guy up in there. So this is 22.36 radians per second. That number times our time is going to complete our equation. We have one unknown in this entire equation. We divide both sides by 0.05. 0 divided by 0.05 is still 0. So we have the cosine inverse of 0 is going to be equal to 22.36 radians per second times our time. So our time is going to be equal to cosine inverse of 0 divided by 22.36 radians per second. Now this is the first time this semester that you have got to be very careful about what your calculator is set to. So when we're doing this, this guy right here needs to be in radians, because the numbers that we're going to be putting into it are in radians. So with that, in this case we've got 0, but we need to get a number out in radians. Sorry, the numbers we put into it are not in radians. We need to get radians out because we're dividing by radians per second, so we can't get degrees out, otherwise it won't work for us. So when we solve this for our time, it is still going to come out to 0.07 seconds. So a lot of the time this is what you have to use. I went ahead and used a simplified way of getting there just because we knew it was coming to a very consistent point. In this case, we were lucky. We could skip that, but that's not always going to be the case. So this guy, we're going to call t at 1, and that is going to be equal to 0.07 seconds. Okay, next piece. Let's talk about the velocity at time 1. Velocity at the time 1, we are going to need to use our equation in order to solve. So we have our velocity at time 1 is going to be equal to our velocity max negative the velocity max times the sine of omega t plus phi. Phi still being that offset and phi still being 0. Velocity max is going to be simplified into a omega s. Still got to keep that negative in there. Sine of omega s times our time at 1. Okay, there we are. Now with this, we can say our velocity 1 is going to be equal to negative. Our a is 0.05 meters. Our omega s is 22.36 radians per second. And our sine omega is still 22.36 radians per second. And we have to multiply that by our time at 1, which we just found to be 0.07 seconds. Sorry, a little bit off the board there. With that, when I plug all this into a calculator, I get my velocity at 1 of negative 1.118 meters per second. So that is negative 1.118 meters per second. And does that make sense? Well, we started here, we're getting to here, it's moving this way, it's going to have, when it hits here, it's going to keep going past it until the spring stops it and pushes it back. But at this point, it is moving that way, which is going to mean we have a negative velocity. Sorry, all of this is set up such that this is going to be our positive direction. Our fully stretched spring is always going to be in our positive direction. So there we have our velocity. Kinetic energy at 1, well, that's just going to come out from our kinetic energy equation. So this is still review. Got 1/2 mass times velocity squared. So this is going to be 1/2 our mass of 0.5 kilograms. Our velocity, negative 1.118 meters per second. Squaring that. Throw that all into a calculator. I should get a value of 0.3125 joules, which makes sense because at this point our delta X is 0, meaning that our spring potential energy is 0. So all of our energy needs to be conserved. Kinetic energy, potential energy from here, there, is becoming kinetic energy down here. They should be the same number, and they are the same number. Again, you might plug in these numbers in, get a slightly different number, but that is just going to be some rounding errors. But they are going to be the same. Okay, last part of the problem. So that first part is really focused on kind of showing you how this works, and we're using some stuff that we already kind of understand to throw that in there. At this point, we're going to actually start working with a lot of problems that you're going to see more often, where it's where is it at this given time? Most commonly asked question. So at this point, we're going to go ahead and throw in our equation. X at time 2, well, technically it's a delta X. Delta X at time 2 is going to be equal to our amplitude times our cosine of omega t plus phi. Keep writing that phi up and we keep crossing it out. And this is going to give us a value of our amplitude being our 0.05 meters. Our cosine of omega being our 22.36 radians per second. And our time being 0.1 seconds is what we're after. 0.1 seconds. And that is going to give me a displacement at time 2 of negative 0.031 meters. Okay. That's our number. Does that number make sense? Let's check. Well, our total period, the time for it to go all the way in and all the way back out, is 2.81 seconds. So we have not gone a full back and forth yet. We've only gone 0.1 seconds. We're a little under a third of the way, and a third is less than a half, so we haven't made it all the way back here. But we have made it past a quarter, which was our 0.07 seconds. So we are in the negative side. We're in the negative side, 0.031 meters. Makes some basic sense there, so we're doing okay so far. With this, our next step, our potential energy at 2. I should probably change this to potential energy spring, just so we don't have any confusion there. But our potential energy spring at 2, we said was 1/2 k delta x squared. 1/2 times 250 newtons per meter times delta x, which is negative 0.031 meters squared. That value comes out to 0.119 joules. Well, that's not equal to our previous pieces, and that's not equal to our previous pieces because we have part of this as potential energy and part of it as kinetic energy. We're still going to have a velocity. So let's find that velocity. Our velocity at time 2, sorry, let me write that up here quick, 0.119 joules. Our velocity at time 2 is going to be equal to negative a omega sine of omega t plus phi. Phi is still 0. So we have negative 0.05 meters. That's our maximum displacement. That's our amplitude. Omega of 22.36 radians per second. Sine of 22.36 radians per second times my time, 0.1 seconds. Just barely off the board again there, sorry. And that comes out to a velocity of negative 0.880 meters per second. Okay, we're past this guy and we're moving to the left. Moving to the left is going to be negative. We are starting to slow down, so our velocity was 1.118 meters per second when we're here. The spring's starting to act against it, it's starting to slow it down. That all checks out. Now our kinetic energy at 2 is going to be 1/2 mass times velocity squared. That's going to be 1/2 times our mass, which was 0.5 kilograms, times our velocity squared, negative 0.880 meters per second. Square that entire thing. I'm going to get a kinetic energy of 0.193 joules. Marker's dying here a little bit. 193 joules. Let's go ahead and make it so that shows up. So we've got 0.193 joules. We add the two of these together, and I should come out to, so clearly these two are not going to add to this number because there's some rounding involved, but they're going to be very close to my 0.3125 joules. And if you went through and you did not round it all, that is going to be exactly what it comes out to, because our total energy needs to be the same consistently. Potential energy plus kinetic energy, we've got no extra work going on here. It's going to be potential energy and kinetic energy. So potential energy spring and kinetic energy in this case. We don't have anything else going on. That is one of our spring problems. Funky movement, we have to worry about the cosines. Again, when we're plugging these in, plugging in this sine thing, plugging in this cosine thing, our numbers need to be using a calculator in radians. And you need to have your calculator set to radians, because otherwise it will do it as if this was, well, in this case, 2.236 degrees, which is not the same as 2.236 radians. So it's going to catch a bunch of people. It'll be a problem on the test, but that is something we need to be very careful about. Make sure your calculator is set the right way. With that, take care. See you next time.